Hi, Assalamualaikum warahmatullahi wabarakatuh. We meet again in BHA1113 Engineering Materials. So for today, we are going to look at on the new chapter, which is chapter 3. And by the end of today's topic, students should be able to explain and analyze the mechanical properties of the materials. Number 2, you should be able to differentiate different types of mechanical testing for each materials. As for the lesson objective, at the end of the semester, students should be able to analyze the physical properties of engineering materials and concept of corrosion and metal alloys microstructure, phase diagram, as well as heat treatment processes. Now let's look at the topic for today. There are two major topics, which are mechanical properties and number 2, mechanical testing. Under mechanical testing, there are few testing that we are going to learn. However, for today's lecture, we are only going to cover on tensile test, and the rest of other types of testing we are going to look at on the next coming lecture. In mechanical properties of materials, things that we need to address and we are going to learn is that, like, stress and strain, what are they and why are they used instead of load and deformation. Number 2, the elastic behavior, why loads are small, how much deformation occurs, what materials deform the least. And number 3, plastic behavior, at what point does permanent deformation occur, what materials are most resistant to permanent deformation. And last but not least is the toughness and ductility. What are they and how do we measure them? Now let's look at our first topic for today, which is mechanical properties of materials. And these are the terminology that is going to be used in this topic. So familiarize yourself with this term, and if you still do not understand on the deformation that have been explained here, you may also Google or watch on YouTube in order to understand what are these terms meaning. This table showing you a relative mechanical properties of materials at room temperature, like strength, hardness, toughness, as well as stiffness. And if you look at these two tables, the value of those mechanical properties moving downward or decreasing with different types of materials, starting like fiberglass, graphite, anti-lead, and this one from ductile materials, anti-thermoplastic, and so on and so forth. So it shows that basically different types of materials have different types of properties, even though it is at the same room temperature. What is elasticity? Elasticity is the ability of a body to resist a distorting influence and to return to its original size and shape when that influence or force is removed. Solid objects will deform when adequate loads are applied to them. If the material is elastic, the object will return to its initial shape and size after removal. If you refer to this figure here, you can see that this one is initial shape, and after the load being applied to it, there's a deformation. Deformation occurs on that materials or specimen. After that, when that load being released, it returns to its original condition, which means that elastic deformation is actually reversible. So whenever you apply either linear elastic, linear types of load or non-linear elastic of load, it will still come back to its original form. What about plasticity? Plasticity is the ability of a solid material to undergo permanent deformation, a non-reversible change of shape in response to applied forces. If you refer to the illustration here, this one is the initial condition, and then figure number 2 showing the load being applied until plastic region. After that, even though the force has been released from that material, the material doesn't go back to its original form. So we can say that plastic deformation is actually permanent. In mechanical properties of materials, there are things that you need to know, which is known as engineering stress. Engineering stress is the applied load divided by the original cross-sectional area of a material, also known as nominal stress, and it can be divided by two, which is known as tensile stress sigma and shear stress tau. The formula is the same, which is area over A. However, the only difference is that the direction of forces acting on that area. For example, for tensile stress, the area of forces acting on the direction of forces acting on the area is actually perpendicular to the surface area. However, for shear stress, the direction of forces here, Fs, working perpendicular to the surface area. So that would be the only difference between tensile stress and shear stress. We may find these types of application of stresses in cable, for example. There's this one, the free body diagram for the cable. In static, you've learned on how to find the value of forces reacting on cable, or it's either directional, unidirectional forces or torsion, which acting on this shaft for this case. And formula to calculate value of stresses or nominal stresses for cable equals to F over A. And for torsion, in this case, shear stress exists on that structure. And formula is the same, force over area. However, this one stands for tau. So there's a typing error there. Another example is bridge. So you can see this one is actually suffering a compression stresses. Other than that, you may also find example application of stresses for in pressurized tank and also fish underwater or even human underwater. For pressurized tank, if you take this example, this specimen over here, actually this tank will suffer called as a biaxial tension, because if you look at the free body diagram here, there's a two directional forces acting on it, which is in y direction and also x direction. Whereas for fish underwater or human underwater, it suffers hydrostatic compression, whereby in this case the specimen will have stresses or pressure or forces acting on every single area of that specimen. This one is showing you on how to calculate the tensile strain, lateral strain, and shear strain. And please be noted that strain is always dimensionless. And in material science and engineering, this is the calculation or the knowledge on this part is actually introduction or the basic part of it, and the continuation will be, you will see again in strength of materials 1 and also strength of materials 2. Now let's move on to Poisson ratio. In mechanical properties of materials, the other things that you need to know other than plasticity, elasticity, stresses, you also need to know what is Poisson ratio. Poisson ratio is defined as the ratio of the change in the width per unit width of a material to the change in its length per unit length. And if I take an example of a rubber with a cylindrical shape, and then I'll pull it outward, and you'll see that the dimension of the cross-sectional area of that rubber will decreasing. Same goes to its length, whereby its dimension will be thinner, will become thinner and also longer. So that's that's the meaning of Poisson ratio, and the value is always negative because it shows that it is in they shrink in condition. And the value of Poisson ratio normally between 0.25 until 0.4. If Poisson ratio equals to 0, it means that the width of the materials doesn't change when it is stretched or compressed. However, if the material is getting thicker when it is stretched, then value of Poisson ratio normally less than 0. The example of value for Poisson ratio in stainless steel normally 0.28, whereas for copper 0.33. And again, this is the formula on how to calculate the Poisson ratio with its normal value of ranges for materials. So again, in engineering stress, there are tensile stress and shear stress, and the formula is P over A. Other than that, the engineering strain, which is known as epsilon, equals to L minus L naught divide L naught, or different in L, different in length, divide by its original length. Okay, now let's move on to topic number 2, which is mechanical testing. So the first types of mechanical testing that we're going to look at today is tensile test. These figures here showing a typical tensile test machine as well as a tensile specimen. And this one, the typical type of machine that is used in our lab, which is also known as universal tensile machine. This is where you put your specimen, or the specimen being held over here. This is as the load cell, whereby it used to apply load to the specimen until it breaks. So how do we prepare this specimen? The specimen need to be prepared according to the standards. It's either ASTM, GIS, ISO, and so on and so forth. And the shape of the specimen will be different depending on the standards that is going to be used. For example, for this one, it is in circular or cylindrical dog bone shape, whereas this one is a flat dog bone shape. Nonetheless, even though despite of the shape of the materials or specimens being used, or standards being used, the results will be something like this. Yeah, this is the typical stress strain curve. This is the y-axis represent the stress, and x-axis represent strain. And other than stress strain curve, we also can get load tension data as well as stress strain data from tensile test. In tensile test, there are mechanical properties that is very important for us to know, and there are includes elastic modulus or Young modulus, E, yield strength, and ultimate tensile strength, UTS, elongation at fracture, as well as reduction in area at fracture. So this is the typical stress strain curve. If you look at this figure here, there is elastic region over here. This is elastic region, and this is plastic region. Now let's look at the first region, which is elastic region, starting from point here until point Y, or yield stress point there. If let's say a value of force is given to the structure, to the specimen up to this point, and then you release it, that specimen will go back to its original form following the continuous line over here. After that, you increase a little bit the value of forces there, then it will go up again until up to this point. Once you release the value of stresses, value of forces there, then it will go back to its original form following this continuous line. However, when you keep increasing the value until it reaches this point, which is yield stress point, then you release the value of the forces over there, then it will still come back to this point. However, it will no longer following a continuous line over here, but it will follow the dotted line over here, which is a little bit offset than its original line, with the value of 0.2% offset. So whenever it reach point yield stress over here, it won't come back following the continuous line over here. Okay, so now once it reach this point, it will turn into plastic region until it reach to the maximum point, which is known as ultimate tensile strength, UTS over here. After this point, you keep increasing the value of forces. It will start necking until it reach fracture, and finally the specimen is fail or break. Now let's look at the illustration. This is the original form. Then you give forces over there until this point it start to elongate. After that, after UTS, we will start to have necking over here before it break, and then reaching that point of fracture, then it will break. Okay, so now let's look at the properties of the tensile test. Number one is Young modulus or elastic modulus. The formula is that sigma equals to E epsilon, and this one also known as Hooke law. If you refer to stress strain curve, the value of Young modulus can be obtained from the slope of the diagram. And the higher the value of Young modulus, the higher the value of Young modulus, it means that the materials have higher bonding strength. So it will be much more difficult for that material to break. If you refer to this table here, you can see that the diamond is the most strongest materials among other types of materials like those in metal alloys, polymers, or ceramic. However, even though it is strong, but doesn't necessarily it is tough. Number two is yield strength. Yield strength, the point that it reach, the point where before it turn into plastic region. So or in other words, it refers to the last point for elastic region. And as mentioned to you just now, once it goes back to the original form, but still there's a little deformation occurs there with an offset of 0.2%. Offset yield strength. And if you calculate the deformation happen in that specimen by taking example of 2 inch of this specimen in length, you'll find there's a changes of 0.004 inches in that specimen. And this table here showing the comparison for yield strength with among different types of materials. And if you look at here, metal alloys normally produce the highest yield strength as compared to the rest of other types of materials. And number 3 is ultimate tensile strength or UTS. And this point, after this point, necking starts to occur until it reach fracture. For metal, UTS occur when noticeable necking start, whereas for polymers, UTS occurs when polymer backbone chains are aligned and about to break. This table, this graph showing a comparison for tensile strength for different types of materials. So you can see what are the value for metal alloy, graphite, polymers, composite, and so on and so forth. Number 4 is ductility. You see those materials who may deform or elongate after certain types of forces being introduced to it. Before fracture, it elongates or deforms, then you know that material is known as ductile. Whereas if that materials sudden break, straight away break after the load being applied to it without any deformation, that one is known as brittle material. Even the structure itself different. The structure failure is different compared to brittle and ductile material. For ductile material, it will have necking, whereas for brittle material, the fracture surface perpendicular to the stress. And number 4, this is still ductility, and this is how you calculate the value of ductility. Is either using the value of length or using the value of area. And if you look at to this graph over here, brittle material will have smaller will have smaller ductility, whereas for ductile material will have larger ductility. So that one, I think, is very common sense. You may compare it with like with metal and also composite or plastic. Metal is actually much more ductile as compared to plastic. Number 5 is toughness. Toughness refers to energy to break a unit volume of materials, and for ceramic, it has small toughness. Metals have large toughness. Polymers has very small toughness. So several different types of materials have different toughness. So it doesn't mean, like I mentioned just now, even though metal have high strength, but it doesn't mean it is high in toughness. Number 6 is resilient. It refers to the ability of a material to store energy, and this is the formula for resilient. However, in this subject, we are not going to focus on resilient, but then this is a basic knowledge for you in order to know what is resilient. And these things you are going to learn more in strength of materials 1 and strength of materials 2. Other than that, you will also need to know what does it mean by true stress and strain. Well, the formula is the same even though for stress or strain. However, the difference is only that, for example, true stress, force over area, but then the area actually refers to the changing area with respect to time of the specimen at that load. So same goes to strain. It refers the value of A there actually refers to the changing area with respect to time of that specimen at that load. And if you refer to this graph here, it stated that true stress is always greater than engineering stresses. Okay. Other than that, you may also want to refer to this table because it shows you different types of materials obviously have different types of true stress and strain. Like for example, if you may refer here like stainless steel, brass, copper, aluminium, and so on and so forth. Stress strain curve also may be affected by temperature. For example, what will happen to the what will happen to the curve when temperature being added is that, number one, it will raise the ductility and toughness of the material. Now, B, lower yield strength and the modulus of elasticity. 3, lower the ultimate tensile strength. And number 4, lower the toughness of the materials. Other than that, rate of deformation also being affected with the temperature. For example, if you look at this graph over here, the higher the strain rate will be, then the higher the strain rate is, then the higher the tensile strength will be. Meanwhile, this table showing a typical ranges of strain and deformation rate in manufacturing process, you can see that there are several types of processes over here, like cold working, forging, rolling, explosives, forming, forging, extrusion, and so on and so forth. And this process produce different value of true strain as well as deformation rate. So it doesn't matter. It doesn't mean that even though different types of materials, it doesn't guarantee it will produce same value of true strain or deformation rate if we use different types of processes for the same types of material. Now let's see the example for today's topic. Exercise number 1 asks you to calculate the engineering stress in SI units on 2 cm diameter rod that is subjected to a load of 1,300 kg. So how do we solve this problem? Number 1 is that we need to convert the load to a force using the SI units. So formula is F equals to MA. So substitute all the information given into the formula, then you'll get the value of A equals to 12,753 Newton. And then apply this formula, which is stress equals to force over area. And area, diameter is given to you, then you should be able to find the value of area. After that, you'll get the value of stress equals to 40.6 megapascal. Now let's see example number 2. Question asks you to calculate the engineering stress in SI units on a bar 15 cm long and having a cross section of 4.25 mm times 12 mm that is subjected to a load of 5,000 kg. So basically this shape is a rectangular shape, and the first thing that you need to do is convert the load to a force in SI units. Formulas given is F equals to MA, and just substitute all the information into the formula, then you should be able to get the value of force equals to 49.05 kilonewton. After that, just substitute into the formula of stresses. This one is not F, this is for sigma actually. And just substitute the information into the formula, you should be able to get the value of sigma or stress is equals to 9.62 megapascal. Now let's look at exercise number 3. A tensile specimen of cartridge brass sheet has a cross section of 10 mm times 4 mm and gauge length of 51 mm. Calculate the engineering strain that occurred during a test if the distance between gauge markings is 63 mm after the test. Do you still remember the formula for strain? Okay, so this is the formula for strain. So now we can just key in the information by using the statement over here. Then you should be able to calculate the value of strain, which is equal to 0.235. And let's look at next exercise which is exercise number 4. A 0.5 mm diameter round sample of 1030 carbon steel is pulled to failure in a tensile testing machine. The diameter of the sample was 0.343 mm at the fracture surface. Calculate the percentage of reduction in area sample. Formula for percentage reduction in area is given such as follow. Then you just substitute all the information into the formula. Finally, you should be able to get the percent reduction in area equals to 52.93%. And for exercise number 5, 6, and 7, you can do it on your own. You don't have to submit to me. This is only an exercise to you in order to make you familiarize with the calculation and to give you more understanding on how to calculate it. And if you still don't understand, you may refer it to me. It's either in a group or in Google Classroom. Yeah. So I'll give you a few seconds to copy this slide. Done? Okay, cool. So now let's move on to exercise number 6. Please copy this exercise. All right, moving to exercise number 7. Well, for exercise number 7, you don't have to do the calculation. You just need to explain why does it happen like that. However, if you still need to use a formula or calculation, yeah, you may put any assumption value in it. Okay, so now let's move on to exercise number 8. Based on the table below, number 1, which has the greatest reduction in area? Number 2, which is the strongest? Number 3, which is the stiffest? And number 4, which is the hardest? Well, I give you a few minutes in order to think. Then afterwards, we are going to answer it together. Okay? All right, so now let's see whether your answers are correct or wrong. Number 1, material B will experience the percentage area reduction since it has the highest strain at fracture and therefore is most ductile. Number 2, material D is the strongest because it has the highest yield and tensile strength. Number 3, material E is the stiffest because it has the highest elastic modulus. Stiffness equals to E equals to sigma divided by epsilon. The higher the value of E, the more stiffer the materials become. Number 4, material D is the hardest because it has the highest tensile strength. And these problems or additional exercises, you may do it on your own. And if you don't understand, then you may refer it to me. Well, basically, the list of problems here, things that I've explained to you just now, it is basically the summary of what you have learned for today. So it is good for you to answer this question to make you understand more. All right. Same goes to this one. Please copy this question as well and try to plot the graph. After that, answer the question. Again, if you don't understand, yes, you may refer to me. Okay. As a summary, for stress and strain, there are such independent measurements of load and misplacement respectively. Number 2, for elastic behavior, the reversible behavior often shows a linear relation between stress and strain. To minimize deformation, select a material with a large elastic modulus. Number 3, for plastic behavior, this permanent deformation behavior occurs when the tensile uniaxial stress reaches sigma y. This one sigma y, there's a typo there. And for toughness, the energy needed to break a unit volume of materials. And last but not least is on ductility, the plastic strain at failure. With that, thank you very much for your kind attention and time. We shall meet again in the next lecture with the same topic, chapter 3, but then part 2. So if you do have any problem related to the topics, in case you still don't understand, you may refer it to me either through WhatsApp group or Google Classroom. With that, I thank you very much and see you again in the next class. Bye.